So as I said, the yaw control is kind of like this. You have the fuselage, and then you have your vertical tail, and then you have the control that will kind of can change direction. And if you move it like this, right, then you might actually, for a positive del R, you might actually generate a delta lift in this direction, right? So what you can really say is that the lift, CL lift of the vertical tail, is really a function of the side slip that the airplane will see, but it will also be a function of del R, right? So, and this is like the partial derivative of the change of the lift at the vertical tail as a function of del R. So you add them two together, you obtain the CL, the actual lift that you will get from the vertical tail, right? This is kind of the situation. So when I write this, Cn vertical tail is equal to minus CL Vt times Vv times Vf divided by V infinity. If I really like that, write it like this, then you need to be aware that this also here includes the control. Okay? It's not only the side slip, but it also includes the control. Okay? So what I'm interested now is what happens to Cn vertical tail del R. I'm interested in the partial derivative here. Okay? So the partial derivative would look like this, minus the tail volume ratio, which is a constant, right? It will be there. Vf, or V vertical tail, sorry. V vertical tail divided by V infinity square times now del CLF, or vertical tail, divided by del R. Okay? And this is the sensitivity now. How big is your lift versus del R, right? This is that sensitivity. So Cn for the vertical tail is then simply Cn beta times beta. And now I'm leaving out the vertical tail subscripts over here, the vertical tail, plus Cn del R times del R, right? This is because of the side slip. And this is because of the vertical tail. Okay? Vertical tail and the side slip. So in trim, okay, in trim, what happens is that Cn must be equal to 0, right? Cn must be equal to 0, which really means, you know, beta is equal to 0 and del R is equal to 0. So that's what happens in trim. That's a typical trim condition. Typical trim condition. Okay? But let's say you want to trim this vehicle. Let's say you want to, first of all, you have any questions on any of these things? On this? The control? Yes, please. This one here? This is because of beta and del R only. Cn because of del R and beta. Cn generated because of del R and beta. In other words, if you know, Cn might be generated because of other reasons. There might be a yawing moment because of other reasons. The Cn we are talking about here is the Cn because of del r and beta. Is there a beta because of the vertical fin? This is the Cn we will get. If there's a del r, the rudder, this is the Cn we will get. If there's anything else that causes a moment, it's not included here. I could have easily written Vt. That's fine. If you want, I can write it. Anything I'm writing here is the yawing moment because of the vertical tail. Does that make sense? So in other words, I included the side slip and the vertical tail. I could have included other things. Then maybe I might want to remove this Vt. Does that make sense? Any other questions? Okay, so in trim, we definitely want these to be 0. Okay? So here's then the question. What if the airplane wants to indeed fly in a side slip? What if the airplane indeed wants to fly in a side slip? In other words, let's say beta is not equal to 0, and we want to fly in side slip. Could this be a trimmed flight condition if you fly at constant velocity with a side slip? It's a trimmed flight condition, right? So what is the trim condition then? So what we are talking about is beta is not equal to beta 0. So beta is equal to some beta trim value. Let's say I want to fly with a side slip of 10 degrees. Okay? But in trim, Cn still must be equal to 0. Cn must still needs to be equal to 0. Well, that's the definition of trim, right? Moments and forces are equal to 0. That's the definition. Cn must be equal to 0 in trim. So this is now in trim. Cn is equal to 0, where now Cn beta times beta is equal to beta trim, so it's not equal to 0, right? I mean, this is we are trying to fly in trim with some beta, plus Cn del r times del r trim. So the pilot has to now input something because you have this and this needs to be equal to that. So how much control must the pilot input? Now this is something I can calculate now. Delta r trim, so this is the pilot input, is equal to minus Cn beta divided by Cn del r times beta trim. You see? I mean, it all comes from this thing here. Let me put a little further. It comes from this. If Cn is equal to Cn beta times beta plus blah, 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 that means that in trim with side slip, this is now trim with side slip. Trim with side slip, the pilot must input this amount of rudder in order to keep it in trim, because only then will this be equal to 0. And note that for a positive beta, you need a negative control here, and this is a negative one. So you could calculate this. You can calculate how much control you can put in order for this to be in trim. Now, of course, the control over here of a rotor, of a vertical tail, it has a certain limit, right? I mean, this angle has a certain limit. It is not going to infinity. I mean, it has a certain limit. So then you can calculate what is the biggest beta this airplane can fly given the maximum input on your rudder. Okay, if this is a limit, let's say this is del r max. So if this is the maximum number, I could calculate what is the biggest beta that this airplane can fly with. So in that case, it would be like this. 0 is equal to Cn beta times beta max. This would be the maximum beta that this can fly, times Cn del r times del r max. So, and here you can calculate now quite the opposite. You go the opposite way. You calculate beta max, okay, Cn del r, Cn beta times del r max. So if I design an airplane and I know my delta R maximum, how much deflection I can put on the vertical tail, I can actually go back and tell what is the maximum side slip I can actually endure during flight. Okay? Is that okay? Does it make sense? All right. This is as much as I want to say about yaw control. I want to move into roll control, which is a little bit more involved. This is kind of straightforward, the yaw control. Any questions? Okay. The next thing I want to look at is roll stability. Okay? And this topic is kind of important because it is not as straightforward. What the roll stability really wants or asks for is the following. Let's say I have an airplane that is flying at wings level. Okay, wings level flight, very nice. Phi is equal to 0. You're in straightforward flight. For whatever reason, the airplane, let's say, rolls. Okay? So this is my phi angle. It's the roll angle. Okay? And here the roll angle is equal to 0. All right? So that's my roll angle. So, and this is looking from the back. Okay, this is the back view, so I'm looking from the back. So, what we want is, if for some reason the airplane rolls, we want that airplane to roll back, right? We want it to roll back so that it comes back to this flight condition. So, the roll moment is delta L, right? The rolling moment. So, you want to have a rolling moment. So what do we really want? We want, if there is we want a rolling moment versus del phi. That's what we want. Is this a positive phi or a negative phi? If you're rolling to the side and we're looking from the back, is this a positive phi or a negative phi? It's a positive phi, right? Because if this is the back of the airplane, you take your thumb and this is a positive roll, right? X body is in this direction, so that's a positive roll. So that's a positive phi. So a positive phi, you want a negative or positive delta L? Negative delta L, right? For a positive phi, you want a negative delta L. You would like to have a negative. You want this to be negative, less than 0. This is what you want. Okay. Now, physically, when we were looking at the rudder, I could tell when the rudder wants to rotate, like, right? I'm sorry, not the rudder, the vertical tail. We can say why the vertical tail would give you that yawing moment, because it gives you an angle of attack, so if you'll rotate the airplane and so on and so forth, it's there. Can you think of a reason why the airplane would need to rotate back to this flight condition? I mean, physically, can you think of a reason why the airplane should rotate back? What I'm trying to say is that the rudder is here, okay? So if you have this, if you have a side slip angle, because of the rudder, it will come back. So that's a given. And the pilot doesn't have to touch anything, so we say it's statically stable if it comes back like that. That's fine. So if the airplane rolls for some reason, why would it come back? What control surface would rotate this airplane back up here? Aileron is a pilot control. So the pilot can, of course, bring it back. but that is not static stability. Static stability is when the pilot or any interference or the control doesn't move. I hope you know this by now. Stability is without pilot control. The pilot can make it do anything. The problem is, will it come back to the equilibrium point without anybody touching it? Right? Remember the pendulum, right? I can make it, if it's going like that, the pendulum, I can move it here, I can move it there. But the question is, if I don't touch it, will it come back to equilibrium? Right? It's the same thing for the airplane. If I do this, if I don't touch it, will it come back? For the yaw, we know that now, because if for some reason I have a side slip, the airplane will automatically come back. The pilot doesn't have to touch anything. So, question again. If I have a roll, will it come back? Without the interference of the pilot, because that is not what static stability is. Static stability is without controlling, without the interference of the pilot, what will it do automatically? Give a disturbance, what will it do? Right? You do this, how will it come back?
If the lift has a component, it can give them.
Which component? Who?
If it's rolling like this, the main lead.
Yeah, but how? I mean, this is the lift and this is the rotation. Now you rotate. So what now?
So
why will it come back? Huh? No control input.
the lift will be higher on the lower wing?
It will be higher on this side. Why will it be higher on this side when you have an airplane flies like that? I don't know. What about the angle of attack? Explain it to me. Well, you are going in the right direction, but I have to explain a little bit more. The reason, here's the thing. Because of this phi, for the airplane to roll back, there's really no reason. If you have an airplane that flies like this, and you only rotate it like this, okay, there's no reason for it to come back. There is no aerodynamic surface that will rotate it back. Okay? So in reality, this is not really the case. For most airplanes, this is close to zero. Okay? There's no reason, because of phi, for this airplane to come back. You rotate, it will not come back there's no real reason because of phi. Okay? But what happens in real life, in most airplanes, not in real life, in airplanes, here's what happens. Listen, now this is important. You have an airplane like this, and for some reason you rotate. What happens is this. The airplane will start sliding down. It will fall down. It won't fall down like that. It will fall down, slide down. Because of this slide, it will come back like this. And I will tell you in a second, in more detail, why that happens. But this is what's happening on most airplanes. This is what we call roll stability. You roll, for some reason you roll, then you slide down, and because of this slide, you rotate like this. Okay? So if you roll in this way, you will slide down, and then because of this slide, you will roll back. So in other words, you would be doing this. Okay? Roll, slide, come back. Okay? Roll, slide, come back. That's what happens. So when I say roll and I say slide, what does it mean? You have a forward velocity v infinity. You roll, you slide. Slide means you have now a velocity from the side. Side plus this. What do you have now? Side velocity, forward velocity, air velocity. What do you have? You have a beta, right? You have a side slip. So you rotate, you slide. Because you slide, you have a side slip. Because of that side slip, you will rotate. Okay? Now here's a funny thing. When you do this, you slide and you have a side slip. What's going to happen to your control or to your stability? Well, the rudder wants to rotate towards beta, right? So you can't really only do this and slide and make this perfect turn. You actually do this, you slide, but you also rotate a little bit in that direction too. Right? You also rotate towards V infinity. I mean, look at this airplane. You have this. You slide means that's coming velocity from here, but you're also going forward, which means you have now a side slip. Side velocity, forward velocity, side slip. Okay? Okay, because of that side slip, you will roll back, but at the same time, because of the side slip, you will rotate towards the side slip momentarily because of the rudder. So you do this, you don't really have this perfect thing. You roll, you slide, you turn a little bit, but at the same time, you roll back. Why do you roll back? I will tell you in a minute. But that's what's going to happen, right? Roll, side slip, and then come back. So the airplane will be doing, yes, it will be doing this, but every time you have the side slip, you're also moving towards that a little bit too. So you're doing this, roll, and then move, and then roll and move. What does it look like? It looks like the Dutch roll. And we found the Dutch roll by looking at our matrix. We found that mode. So you give that oscillation, it would give you this. And we found it in the matrix. It was in the matrix. But this is now the physical explanation. I give you this. You will slide, you will roll back. But when you roll back, you have a beta. Because of that beta, you will turn towards that thing. And if you overshoot, you will start doing this, and eventually it will turn out and you go in your forward direction. So that's the stability. Okay? So the only thing that I haven't really explained is, why is this airplane sliding? I mean, we know why it's sliding, but when it slides, why did it come back? Okay, that's the question. So that's what I'm going to explain it to you now. Why does it come back? Okay. You had a question?
Your explanation, we lose altitude actually.
Yeah, we use also a little bit altitude.
Is your explanation still valid when we don't lose altitude?
There's no way to slide down without losing altitude. Okay? There's no way you slide without losing altitude. As soon as you do this and you slide, you are losing altitude. The thing is, once you slide a little bit, it's enough for you to make the turn. So it's not like you're falling down a lot. You're doing this. Okay? And you might have seen this, I don't know, maybe if you have seen videos of airplanes, you might have seen the airplane doing kind of like this, under a lot of wind. You might have seen this, or turbulence. The airplane is kind of doing this, you see? It's not like it's falling down a lot. Okay? So it's kind of more like a motion that looks like more like this. Okay? And because of this you're rotating, you kind of are actually doing more like that. Okay? So it's not a lot of altitude change, but there has to be some altitude change. Okay? Any other questions? All right. So, roll stability. Oh, that's that. So, why are we rolling back when we are sliding down? Well, this is what happens. Most airplanes have something called a dihedral. So the wings are not really straight. Okay, this is the airplane looking from the top or from the front, doesn't matter. It has some sort of an angle. Now, I'm putting this angle now I'm exaggerating here a little bit, okay? Even if you look at this airplane, you will see a little bit of a dihedral. It's not like 40 degrees, 50 degrees. It's very subtle, but it's there, okay? If you look at older airplanes, it's a little bit more obvious, the big dihedral angles. So this is what we call the dihedral angle. Okay? And it is always part of the design. And the reason you put a dihedral on these wings is because of what I've just explained, that when you rotate, you want to come back. Okay? All right. So here is what happens. Let's say I have this dihedral. and let's say you rotate with this. Okay. And let's say now you're falling down like this. You're sliding down, and you have a side velocity of v. And this is, of course, the air velocity, right? But note that we are looking from the back. Look from the back. From back. And so we also have the forward velocity. But because we are sliding down, we also have this side velocity. Now here's what happens. Take this velocity vector. Okay, take this velocity vector and look at its components. One is like that, the other one is like that. This one here is like this and like that. You see? You see? I mean, the same velocity vector looks now different on these two wings because of these two angles. This red vector is the red velocity vector coming from the side. It has two components. You can decompose it into something parallel to the wing and something then perpendicular to the wing. Here do you do the same thing, perpendicular to the wing and parallel to the wing. The ones that are parallel to the wing, they are not really doing much, right? But look at the ones that are perpendicular now. You see they are in opposite directions, first of all. And the magnitudes are much different now. This is a really large one, this is a small one, but they are in different directions. So what does it mean for this wing here? The air velocity is blowing from below the wing. What does it mean if it blows below the wing? Let's take this airfoil section here. If I plot this airfoil section here, well, I'm first of all going forward. I have V infinity, right, because the airplane is moving forward. But at the same time, this blue guy here, this blue component, it blows from below, right? So what is the resultant velocity that we are seeing? The resultant velocity here is this one. That's called the resultant velocity. Okay? It went from going V infinity only, because while it was here in this normal flying condition, it had only V infinity, the red one. Now it has the red one plus this plus this blue velocity, and therefore the total air velocity that this cross section will see is now this VR. Why is it there? Because of the blue one. Why is the blue one there? Because we are sliding downwards. So what does this blue one do? Does it increase angle of attack or reduce? Obviously increases the angle of attack, right? The angle of attack is increased. So more angle of attack, more lift. More lift means, yes, get more lift over here. More lift on this side of the wing, because now I have this air coming from below, increased angle of attack, more lift on this side of the wing. Look on this side, what happens here? It's quite the opposite. Take this cross section. Wing. Same V infinity going forward. This is the V infinity coming from forward. What happens to the air? Blows from the top. What happened to the angle of attack? It actually reduced. You see? So because it is reduced, you have less lift on this side. More lift, less lift. You have generated yourself a wonderful moment that will turn you back into the original state. And that happens because you're sliding down. Therefore, you have this velocity coming from the side. Okay? And then you have that moment that rotates you back. If you look from, because this is coming from the side, if you look from the top, while you're sliding down, your airplane looks now like this. Sliding, you have V air coming from here, and you have the forward velocity V infinity coming from that. So you're sliding down, coming from the top. What do you have? You have actually the whole airplane now has some sort of a beta, right? It actually has now a side slip because you're sliding down. You understand that? Because you're sliding down, forward velocity, you actually do have a side slip. So because of that side slip, I roll. If you have this. Okay? Because if you have a dihedral angle. If the wings have a dihedral angle, because of the side slip, you will roll. So what I'm really looking at now is, what is CL beta? So this is the real partial derivative I would like to look at. Okay? This is the partial derivative I'm really interested in. Because if this side slip, if this is a good number, then I will rotate back. Question, is this positive or negative? For a positive beta, do I want a negative CL or a positive CL? Let's start here, over here. Was that a positive beta or a negative beta? If this is backwards, if this is the backwards, if we are looking from the back, so the airplane is doing this, okay, sliding like that. Is it a positive beta or a negative beta? It's a positive beta, right? Sliding like this. So sliding like this, V infinity, velocity from side, positive beta. Okay? Sliding like that, positive beta, positive beta. You see? Okay, it's a positive beta. So for this positive beta, do I want a negative moment or a positive moment? Is this a positive moment or a negative moment? It's a negative moment. X body is in this direction, so it's a negative moment, right? So for a positive beta, I want a negative moment. If that happens, positive beta, negative moment, so this partial derivative has to be a negative number so that I can come back.
Is it moment we are writing lift?
Where do I write this? That's a small l. Small l means moment. Big L means lift. Okay? We don't play with lift. This is a rolling moment, L, M, and N. Okay? All right. So if this is true, if this is negative, then we have what we call roll stability. Okay? That's what we have. Then we have roll stability for roll stability. Do you understand the physical reasoning here? Okay? Every aerospace engineer has to know this. You can't really run away from this. This is something you really have to understand. Okay? Because this is how you stabilize the airplane in the roll direction. We have learned how to stabilize the airplane here. You put the CG to the front and you put a horizontal tail and you have a stable airplane. For yaw, you need this, the vertical fin. And then for this, you really need a dihedral. this. If you don't have a dihedral, then this will not happen, right? I mean, take this case. Take this case. Right? Whatever happens is the same. I mean, the air will just blow the same way along the wings. So there will be no differential lift on the wings. You see? But here, if you have this kind of thing, you will have more lift on one side and less lift on the other side. And if you look at this, the bigger the dihedral angle, the more the difference will be. So if you have a lot of dihedral, you will slide down and you have this really huge moment that will bring you back and probably do that. Now, as I said, the problem here is not really a problem, but this is a fact, is that you have CL beta, but we also know we have something called CN beta. Remember, we just looked at it in the previous hour, right? The CN beta, the yaw stability. Where is it? It was here. We looked at CN beta. CN beta must be positive for yaw stability. Remember? So that means we have this. So which means because of the beta, we will also have a yaw angle. So I told you, you have this airplane. Let's say you have a disturbance in this direction. You roll, you slide down. When you slide down, you have a beta. You generated beta automatically. You rotate towards beta because of the rudder. But at the same time, you roll back. So you kind of do this, right? You're going forward, you roll, and you do this. And if you overdo it, it will start doing that, and that really looks like the Dutch roll mode. Okay? There's one more effect into this whole thing. One more effect. And that's the following. More lift. This is important. More lift means also more drag. It also means more drag. So what happens now? Now you have an airplane. You give a roll. Slide down. Because of this slide down, you have beta. More lift on this side. So you want to do this, but at the same time you get more drag and it will try to rotate you. You see? You're falling down, more lift means also more drag, so you do this. But you were already doing this because of the rudder. But the drag is helping you now because you're falling, you're rotating, more lift, more drag, and the rudder help, you do this. But at the same time, you're here. If you overshoot, then you start doing this, and then you rotate in this direction now. So you give it a nice roll for this airplane. If the pilot doesn't touch anything, the airplane will start doing that. And then eventually it will die out and go straight again. Okay? And that's kind of the Dutch roll mode. We saw it in the equations. Okay, I mean in the matrix. But this is a physical explanation to this whole problem. Any questions? Yes?
What if the roll angle was 90 degrees? Would it roll back?
It would be very difficult. Then, unless you are falling down like that, it would be difficult to come back. So if you're doing this, do this. If you do this, then you will still be hopefully having this. I mean, if you are falling down like that, it will hopefully have that again. It will be the same story, right? It would be the same. Just take this picture and rotate it 90 degrees. So you would have an airplane falling down like that. It will eventually be doing this. The question is, what if phi is bigger than 90? Now that's kind of a difficult question now. You see? That might be a good homework, or I ask it in the exam. Okay, any questions? And this is a story you really have to understand. Okay, if you don't understand it now, go back to the videos, listen to it again, and make that discussion between side slip, sliding down, rolling, and drag. Okay? And it all forms into the Dutch roll at the end. Okay? Any questions? Okay, now, before we go, I have 5 more minutes, so let me just tell you a few more things about this. Well, I told you most of the airplanes, they kind of look like this. But some airplanes really don't like that at all, right? There are airplanes that kind of look like this. I mean, really, the wings are really straight. There are not many, but some of them are like this. The F-16, if you look at the F-16, the wings are really almost straight, right? Why is that? No, you don't want much stability. I mean, you want an airplane, for this airplane, this is a passenger airplane. And for this airplane, yes, you don't want to make this big roll things, so you want to have it quite stable, right? So if you look at this airplane, it does have a dihedral. Look at airplane pictures from the front. I mean, passenger airplanes, they all have a bit of a dihedral, okay? But if you are a fighter airplane, have you seen the F-16s maneuver? Like the fighter airplanes maneuver? They can make turns like whoosh, like that, make whoosh, like that. How can you do it if you have this kind of stability? Right? So you can't really do that. So you want an airplane that is very maneuverable. You don't put a dihedral in there. But then you have to be careful, because if this rotates, it really falls down like this and there's nothing that brings you back. So who's going to bring you back then? Now it's the pilot, right? You're falling down, the pilot will take its control and move it back. Or it might be the autopilot. The autopilot does it sometimes too. If you have a roll control in the autopilot channel, it will do this, and instead of the pilot, the autopilot will move the ailerons in such a way that the airplane will come back. Okay? Yes?
And we have some carrier aircraft which have like
I will talk about that in a second. Okay? First of all, you understand that the more dihedral you have, the more stability you have. And you don't necessarily want a lot of stability if you want a lot of maneuvers. Okay? So it doesn't mean that the airplane cannot be flown. It's quite the opposite. The pilot or the autopilot will help you to reduce this. Even for a passenger airplane like this, of course you fly through turbulence. Do you think the pilot doesn't touch anything? There's a little bit of wind and the airplane is doing this, and waits until... No, the pilot will help to reduce the Dutch roll mode or suppress the Dutch roll mode. Or sometimes it's the autopilot that does that. Okay? You play with the ailerons in such a way that after you do this, it immediately goes back to track. Okay? So this is not static stability. This is actually controlling the airplane to suppress the Dutch roll mode. Okay? So we do design autopilots for those things to suppress these things. Okay? But the pure physics is what I've just explained to you. Okay? So that's that. Now coming back to your question. Let's say I want to have an airplane that is actually unstable. Okay? You could actually build an airplane. Now this has roll instability, which means you have a so-called an unhedral. Okay? The wings are not looking up but down. You rotate and this will actually make you rotate even more. Okay? Is this something good? Well, you decide. Okay? So because something is statically unstable doesn't mean you cannot fly it. The question is, how unstable is it, right? I talked about this in the past. Like your car, when you drive with your car and you're driving with your wheels, right? And then you leave your wheels and there's something on the road that makes you turn, right? And your car starts turning in one direction. What do you say? Oh, my car is unstable, I cannot drive. That's not what you say. You take the wheel and bring it back, right? So it's the same thing for this. I mean, for a fighter airplane like that, let's say you fall down, you're falling down, oh, the airplane is falling. I'll take the ailerons and make it bring back, right? Like this. So you can do it. It's not like it's unflyable if something is unstable. That's not even the case. Okay? Now, this is something you haven't seen much, but you might have seen something like that. Have you seen this kind of airplanes? Okay. So this here, this angle here, we call the unhedral. You might want to say a minus if you are really picky about this, but this is what we call the unhedral angle. So it's kind of like that. So you have probably seen this on airplanes, on large airplanes, where the wings are on the top of the aircraft, right? On the top of the aircraft, you have this unhedral. It is actually there to destabilize the aircraft a little bit, destabilize or help destabilize, stabilize. The reason is, if you have an airplane like that, a large airplane with large wings on the top, and when you are rolling, when you're rolling to the side, like I mentioned to you, you actually get too much stability. I mean, the aerodynamic composition of the wing and the fuselage makes this thing too stable. For instance, you can see that you now have these pockets over here, you see? You might even have these kind of things over here. You have all these pockets on the side, which actually gives you a lot of moment in this direction. Okay? So it makes it too stable if you have really large wings. The composition of the composition of having the wing on the top and the fuselage at the bottom, and you slide down, you have this aerodynamic composition where this airplane produces a lot of moment by itself. So in order to not have this high stability or too much stability or too much moment, you actually put an unhedral to reduce the moment so that the airplane, when it slides down, doesn't have this huge moment and then rotates it back. Because, when you're sliding down and you have a really big moment, you make a big moment, you go in the opposite direction. And you slide down and you have this huge Dutch roll mode oscillation then. So instead of having that, what you do is, you do this, you want to kind of do that, right? You want to ease it out. If you have too much natural stability, you put a little bit of an unhedral. If you have too much stability, like in this configuration, what you do is you make it with an unhedral. You make the moment a little bit less. So what you do is it will come back nicely like that. Okay. So it is actually there to destabilize the lateral. The lateral move, the roll to destabilize the roll stability. Destabilize meaning that it doesn't mean that make it unstable, it just means that reduce the moment that you are getting. Okay? So that's the unhedral. Okay, I will talk about this a little bit more in the next hour, and I want to show you actually pictures of airplanes and look at the wing configurations. You will see there are, you might want to look at airplanes from the front and then from the back with a different eye, with a different vision now. Look at the dihedrals and unhedrals of airplanes, okay, when you go home. But nevertheless, in the next hour, I will show you pictures of airplanes and we will discuss on the unhedral and dihedral configurations on the top and the bottom and all this. Hopefully in the next hour, okay? Which is, I think, not this week, but the following week, because this Friday is a holiday. Okay? So thank you. See you next week.